Hello, in this session we're going to look at the gas laws. Gas laws are the laws which connect the macroscopic properties of gases that we've just been looking at. There are three main gas laws, and they are all presented together in one unified gas law. So this is the penultimate part of the topic, and in particular we're going to be looking, touching on everything that's in bold, but in particular this is the equation of state for an ideal gas that we're going to be looking at, and there's a skill sketching and interpreting changes of state on pressure, volume, pressure temperature, and volume temperature diagrams. So macroscopic properties we have previously looked at, they are pressure, volume, temperature, and the amount of gas. Pressure pascals, 1 Newton per meter squared. Volume in meters cubed, temperature in Kelvin, and that cannot emphasize how important that is. Temperature must be in Kelvin in this equation, in any of the equations using the gas laws. And the amount of gas. The amount of gas, it can't be a mass of a gas because we're talking about an ideal gas, and ideal gases don't actually have any mass. We're talking about the number of particles. And the number of particles, again, is not measured in terms of the actual number, 27 particles. It's measured in terms of Avogadro's number, in terms of a ratio. So 1 mole, which is 1 Avogadro's number of particles, or 2 moles, which is 2 Avogadro numbers of particles. And the thing is that you cannot, particularly if you look at the first three, you cannot change any one of these without changing at least one of the others. Okay, and we'll see what that means in a minute. Now, the gas laws we'll look at in a second, but to sort of start at the end, they all come together in one unified gas law. Initially, different scientists, Boyle, who actually took it from someone else, who actually himself took it from someone else, and Charles and the other guys, Gay-Lussac, all looked at these laws in separation. But what Mendeleev did at the turn of the century, 19th, 20th century, was he developed them and put them together into one ideal or universal gas law. So P pressure, V volume, T temperature, N the amount of substance in mole, and R is sort of the constant that ties it all together, the universal gas constant, which isn't really universal and isn't really a constant, but for an ideal gas it works. So it's important as we go through this that you don't view this as a purely mathematical exercise, but from a physics perspective, I need you to understand why this is happening, what's happening to the actual molecules. And that you have to remember what we looked at in the previous video, that it's all about collisions. It's all about the collisions with each other, collisions with the surfaces, and the transfer of momentum that takes place. We can rearrange the ideal gas law to PV divided by T equals NR. And for a given sample of gas, and this is very common in questions, this is very useful, NR is a constant because for a given sample of gas, as long as you're not putting more gas in or taking any gas out, then N is a constant, R is a constant, so PV divided by T is a constant. And that means that if you look at two different time periods, the same gas sample at two different times, then the pressure volume divided by temperature at time 1 must equal the pressure volume multiplied by volume divided by temperature at time 2, which must equal the pressure volume divided by temperature at time 3, etc., etc., etc. You could do anything you like to pressure or volume or temperature, but that equation, PV divided by T, must always give you the same answer. And we'll look at an example of that in a minute. But what's useful to look at, particularly because it's easier and the subject guide states this explicitly, is to look at just pairs of quantities and how they interact together. So effectively you're holding one completely constant, for example temperature, and you're looking at how pressure reacts with and changes with volume or vice versa. That example is Boyle's law, as it's now known. So in Boyle's law, the temperature is constant, which means that any changes you make must be made slowly, that any energy, any heat generated has time to dissipate. The system has to be in thermal equilibrium with its surroundings. So as long as you hold the temperature is constant, then because P1 V1 now equals P2 V2, if you increase pressure, you must decrease volume. Quite simple. So pressure is proportional to 1 over V, or V is proportional to 1 over P. The graph will look like this curvy graph here. If you want to produce a straight line graph, then you'd have to graph pressure against 1 over volume, or, as I said, vice versa. So that's Boyle's law. The pressure law has constant volume. That's another nice, fairly simple situation. A fixed volume of gas, a fixed container if you like, if you increase the temperature, you increase the kinetic energy of the particles, they increase their velocity, that increases the pressure. So for a given volume, then increasing temperature increases the pressure. Don't forget, it's only directly proportional, which means not only a straight line but going through zero. It's only directly proportional if your temperature is in Kelvin. The final of the three gas laws is Charles's law, Jacques Charles, French physicist, who said, well, what happens at constant pressure? Well, if constant pressure means you've got volume and temperature must be directly proportional. In this situation, you've got a balloon. Now, a balloon maintains the volume it has, whatever volume it has, because of two things: the external pressure, the air surrounding it, and its own elasticity. If you ignore the elasticity aspect and just think about the external pressure, then as the temperatures get larger, then the internal balloon will be temperature means that the velocity of the particles is greater, which means it exerts a greater force on its surrounding, which means a greater pressure, which means it expands. So minus 10, 0, 10 degrees. Volume goes up. So it's a 1 meter cube volume here, less than there, more than there. I do like this diagram. Minus 10 Eskimo. 0 degrees, person taking their life into their hands by trying to skate on very thin ice, and 10 degrees having a barbecue. Yeah, nice weather for a barbecue. Okay, so Charles' law there, volume against temperature, directly proportional. Again, if you have 0 Kelvin, it's got to be in Kelvin. Not quite sure what the boiling point of air is. Air is a mixture, so it doesn't really have a boiling point. Anyway. Now, one thing we can do, because of all this, is we can draw a graph. We've drawn 3 different graphs there. We've drawn temperature volume graphs, pressure volume graphs, and temperature pressure graphs, but you can actually plot one 3D graph. Let me show you actually that being done. If I go to Excel, go to here. So here we have this plot, and the only variable is n. Okay, so for different volumes of gas, different amounts of gas as measured by their number, so up to, well, we can't go as far, but half a mole, set it to half a mole, okay, then you can find any point on this surface is a possible combination of temperature, pressure, and volume. Anywhere that's not on the surface is impossible. Half a mole of gas can never have that combination of pressure, volume, and temperature, which is a bit weird, because you'd like, why? But if you follow these laws, if you follow the gas, if you include that constant, that universal gas constant, which is the key to actually determining what the space that this membrane occupies, but it is a 3D surface, and so it's quite a cool 3D graph, and we can actually look and change the angles here. So you don't need to be able to interpret these 3D graphs. You can just use the 2D versions, but still, I think it's pretty cool. All right, thank you very much.